Good morning, everyone.
Good morning, sir.
Okay, today is lecture number 15 of this advanced concept in steel technology. And today's contents are like this, that is the effect of alloying elements on tempering and temper brittleness. It is also called temper embrittlement. And the last topic, that is temper colors. So, in the previous lectures, we have covered the details about some martensites and also discuss something about this tempering process, what happens basically during the tempering process, why softening will be there during the tempering process, and how the toughness is increasing in the material. So now the topic is effect of alloying element on tempering. So basically what happens, our objective is to improve the toughness, right? So you understand, when we do hardening heat treatment basically, so the martensite which forms is basically harder but brittle in nature, right? But the toughness of the steel is very poor, ductility is very less, lot of residual stresses are there in the steels. So tempering process helps improve the toughness of the material, basically the steels. It also removes the internal stresses, right? But what happens basically, that means, in other way I can say, by doing tempering heat treatment on steel after hardening, we increase the ductility of the materials, right? If when the ductility come into picture, then we have good toughness, right? Because toughness is a combination of good strength and good ductility also, because strength and ductility are opposite in nature, right? But what happens basically, when we are dealing with steels, alloy steels basically, the steel containing alloying elements, right? Not plain carbon steel. So in that conditions, what happens during tempering, the softening will not occur always, or the degree of softening will be not so high compared to that of plain carbon steel. So plain carbon steel will soften easily, but alloy steels will not soften easily, right? There is some problem with alloy steels. We'll discuss that, why it is happening. And another point I would like to mention here, if the temperature is below 150 degrees centigrade during tempering, there is not pronounced effect will be seen in the as hardened steel. That means it will not become soft, right? Because if you remember, there is a range of temperature during tempering. We start with like room temperature to 100, then 100 to 250, then 250 to like 350, then 350 to nearly 700 degrees centigrade, right? Now, the point is, what about alloying elements? So basically, we can categorize the alloying element in steels into two categories, right? The alloying elements which we add into the steels, we can divide them into two parts, two categories. So one, we can divide like this. We can have, see, what is the main role of adding alloying element? The important role of adding alloying element is to improve the strength of the material, right? To improve the strength of the steel. And already we have discussed about the strengthening mechanism in steels upon addition of alloying element. Two things are happening, if you remember. One is solid solution strengthening, and the one is the precipitation strengthening. So that means either you talk about precipitation or you talk about solid solution, all these forms due to addition of alloying elements, right? It basically, it may be interstitial alloying element, or it may be substitutional alloying element, or both of them, right? So we categorize the alloying element into two category. One on the basis of strengthening, how the strengthening is coming into the picture, right? One is solid solution strengthening and one is precipitation strengthening, right? So basically, there are certain alloying elements when they are added into the steels, they increase the solid solution strengthening effect. Why? Because they are forming solid solution. Solid solution, you understand, because they are getting soluble in the ferrite matrix or in the austenite matrix. They're easily soluble. Once they are soluble, it is a solid solution. So they provide solid solution strengthening. So best example I can give is aluminium, manganese, right? Silicon, nickel. If you add those alloying elements, they improve the solid solution strengthening. But because they are because they are getting dissolved into the matrix, ferrite matrix or austenite matrix, right? And there is another category of alloying elements which basically do not dissolve. They may be dissolved up to a very limited way, but basically they try to react with carbon. So they form carbides, stable carbides, or you can call alloy carbides. So basically, when you add those alloying elements and carbon is present in the steel, they start forming alloy carbides or carbides, right? Those are like titanium, niobium, vanadium, tungsten, tantalum, right? Chromium. Tungsten, they react with carbon, form carbides. So you understand, carbide is a precipitate. So they provide precipitation strengthening, right? Now you can see very interesting thing I have written over here. Tempering in high alloy steel. So suppose you are dealing with a steel containing more amount of alloying elements, or amount of alloying element is somewhat higher. What happens? Hardness increases at elevated temperature. So you people understood our objective is to improve the ductility, improve the toughness, or decrease the hardness, or decrease the brittleness of the steel. But this is just opposite phenomenon. You are doing tempering of as hardened steel, and the hardness is increasing. This is very interesting. How it is happening? The same thing happens when I was working on power plant steels in my master degree. So I was also confused. What is happening exactly? When I am doing tempering, after doing a normalizing of my steel to because I have these martensitic laths, right? But when I was doing tempering, I was shocked that why my hardness is initially decreasing with tempering temperature, but upon doing tempering at a high temperature, elevated temperature, my hardness is again increasing. That was a shocking thing for me at that time, right? So the answer is what? Basically, this is the answer: secondary hardening. Hardening due to second phase particles. So precipitates are the second phase particle. Primary phase is your matrix. It may be austenite, it may be ferrite, it may be benite, anything, right? But second phase is nothing but the particles. These are the carbides. So same thing happens with me, because in my steel I have this vanadium, titanium, niobium, tungsten. They form chromium. They form stable carbides at high temperature. So you understand, when you do tempering at an elevated temperature, these carbides start forming into the steels. These are the second phase precipitates, right? So if you remember, precipitation strengthening will be happening because this location will move, and this location will get pinned by this precipitates, if you remember. But in case of carbon steels, this do not happen because there is no carbides, basically, right? And there is an interesting line: alloy carbides are more stable than cementite. So this is a very good thing to remember. Alloy carbides are more stable than cementite. You have to remember, suppose you have a steel and that steel is having precipitates of cementite, cementite networks or cementite particles. They are not stable actually. If you take the steel to a high temperature like 750 degrees centigrade or above 750, basically, they will become soluble in the austenite phase, right? Because they are unstable, they get soluble. But just opposite, if we have carbides, nitrites, right? Oxides, forget about oxides, they are insoluble basically. But if you have carbides, nitrites, precipitates, they are basically stable even at high temperature. You can go to 1000 degrees centigrade. Sometimes if you have niobium carbides, vanadium carbides, you can go to 1200 degrees centigrade. Those carbides are stable even at 1200 degrees centigrade. They will not get soluble in the matrix, right? So that's why they provide strengthening. So that is the reason why hardness increases upon tempering at elevated temperature, right? Now, for that, I have this one, cementite versus alloy carbide. So you can easily write cementite is stable at low temperature, but alloy carbides are stable at very high temperature in steels. Stable means they will not get soluble. So cementite will get soluble, like if you take the steel to 750 degrees centigrade. But that means above 650, it is started getting soluble in the austenite matrix or in the matrix, right? But alloy carbides can go up to 1250 degrees centigrade, 1300 degrees centigrade, like that. So the thing is what? There is a very interesting thing here. You can just look at this one. Just read this one. This is very interesting. Formation is diffusion based phenomenon. So these precipitates which forms in the matrix of the steel are formed due to diffusion mechanism. If diffusion is happening, precipitate will form, right? So what happens basically? Formation is diffusion based phenomenon, and diffusion rate of alloying element is very low at low temperature, and at intermediate temperature it is sluggish. Sluggish means very slow. So that means since, and for this one, just this statement, you can see this is also the cementite formation is also diffusion based. Formation is diffusion based phenomenon. Diffusion rate of carbon is good even at low temperature. Since the rate of diffusion is higher at low temperature for carbon, so cementite easily forms. But in case of alloying elements, diffusion rate is very slow. So they do not diffuse much. If you go to a very high temperature, the diffusion rate will be increased, then the alloy carbides will form. So this is the thing. So you understand this is the main reason behind the formation of alloy carbides at elevated temperature during tempering, and which leads to increasing in the strength and hardness value of the steel, right? So I think this part is clear. Then we'll move to temper brittleness. This term temper brittleness is also called temper embrittlement. Temper embrittlement. See, temper embrittlement. You people understood. These are two terms. Temper, brittleness. Temper terms comes from tempering process, just after hardening, right? Brittleness comes because the material after tempering become brittle. Brittle means just opposite, you can say it has very poor ductility, or you can say toughness get reduced, right? So these are two terms, temper, brittleness. So that means there are certain kind of steels we have, basically steel containing impurity elements, like this one. You can understand, like if your steel contain phosphorus, antimony, tin, arsenic, right? These are impurities, phosphorus, antimony, tin, arsenic in steels. Or suppose steels contain some alloying element like nickel, manganese, chromium, silicon. Nickel, manganese, chromium, silicon, these alloying elements. So this temper brittleness or temper embrittlement happens in case of steels which contain impurities and which contains basically these alloying elements, right? So you understand there is a certain temperature range. If you hold the steel at that temperature range, like this is 400 to 600 degrees centigrade or 650 degrees centigrade. So that means if you are doing tempering just after hardening and you are holding the steel at a temperature of 400 to 650 degrees centigrade, the steel become brittle. Instead of softening, instead of tough, in the increase in toughness, the toughness will reduce. It becomes brittle. So that is called temper brittleness. And it also happens when we cool the steel from the tempering temperature at a very slow rate. So it becomes, so exact reason is not understood till now. But, and the interesting point is this one. Temper brittleness doesn't affect the other mechanical property. even if the toughness is getting reduced, but the strength will not vary, the hardness will not change, the fatigue strength will not change, ductility will not change basically, but toughness will get reduced here. And the important point is this one: molybdenum, titanium, zirconium suppress the temper embrittlement in steels. Suppose you think that your steel is going to show temper embrittlement or temper brittleness during tempering process, you can have these alloying elements. If these alloying elements are present, molybdenum, titanium, zirconium, then it is okay. They suppress the temper embrittlement basically. Temper. So this is the last topic we'll discuss, that is temper colors. So you people understood temper colors means we will see a variety of color on the surface of the steel while doing tempering. So hardening is done, right? Just after hardening, you are doing tempering. The moment you are doing tempering, if you carefully look at the surface of the steel, it will show different colors at different temperature. Starting from the low temperature to a high temperature, you will have different colors, right? The color will change when the temperature will change. If you go to a high temperature, the color will change. If you go to a more high temperature, the color will change. Similarly, if you do holding of also, if you do a lot of holding, if you give more holding or soaking time, the color also changes. The color changes from starting, the color is basically yellow color. The color will change from yellow to light yellow, then brown, then purple, then dark blue, light blue, gray, gray purple, gray blue, dull gray. So the basically yellow, purple, blue, and gray. These are the major colors. You'll see. This color starts from the low temperature. This gray color is at a high temperature. And what is the reason behind the appearance of these colors? The reason behind the appearance of these colors is basically due to formation of oxide film. The iron oxide will form if you do tempering in normal atmosphere without using any argon or nitrogen atmosphere. If you do tempering in normal atmosphere, that means oxidizing atmosphere, oxide layer will form. This oxide layer have various colors. And thickness of oxide layer will decide what color you will able to see during the tempering process. So that means more is the thickness, you will get more different colors, right? I'll show you a very interesting image. You can see these are the different tempered samples. This is the initial tempered, this is some intermediate, and this is the final tempered. You can do tempering for a high temperature also. These colors are visible when we are doing tempering of tool steels. Suppose we are dealing with tool steels where tempering is also obviously essential, because if you not do tempering, then tool will break because the martensite form is brittle and having residual stresses in it, right? So upon tempering of tool steels to get some toughness, so you will be able to see different colors: yellow color, blue color, dark blue, light blue. You can able to see. And here this is somewhat brown. This is yellow. This is brown. This is purple. This is dark blue. This is light blue, right? And some interesting factor here. You can see different temperature, the color is changing. You can see. And there is some interesting fact also. By looking at the color, you can say this is good temper, or this is light temper, like that, or full temper. You can see here it is written over. If you want high toughness, that means good temper. So if you have nice dark blue color, this one, nice dark blue color, that means it has high toughness. If you have very light yellow color, there is light temper, like this. And full temper means you have dark red or light blue, like this. So this is all about your tempering process. So we have completed the topic of this heat treatment. Already we have discussed about annealing, different annealing process, hardening, normalizing, and tempering processes. And also we have discussed about what are the objectives. So I'll end the topic here. If you have any doubt, you can ask me right here.